Okay, let's do an example with both charging and discharging of a capacitor. So let's say that we have a circuit that looks like this. Okay, so the EMF, we have an R1, we have an R2, and we have a capacitor. So let's say the EMF is 25 volts. Let's say that R1 is going to be 250 ohms. Let's say that R2 is going to be 350 ohms. And let's let the capacitor be 50 microfarads. So let's make it 150 microfarads. Okay. All right. So now I'm going to say, first of all, the switch is open. So what's the current and voltage and everything? So if at first the switch is open, then that means that the current in, we'll call this current 1 this way and current 2 that way, that those are equal to 0. The voltage on resistor 1 equals the voltage on resistor 2, which equals the voltage on the capacitor. That's equal to 0. So the switch is open, everything's 0, everything's uncharged. Now I close the switch. So now what happens? The switch is closed, and I want to know the instant I close the switch. The instant I close the switch, what is I1, what is I2, what is voltage 1, voltage 2, and voltage on the capacitor. Now, the instant that I close the switch, then this connects up. This is an equipotential, so the voltage from the top to bottom of that resistor is going to equal the EMF, so that's going to equal 25 volts. Okay, now the voltage here is also going to be 25 volts, but that's V2 plus VC. That's equal 25 volts. Now, the thing is, when you first close the switch, how much charge is on the capacitor? None. If there's no charge on the capacitor, the voltage on the capacitor is 0. So that means that V2 is 25 volts. Okay, so that means that we can see the voltage on resistor 1 is 25 volts, voltage resistor 2 is 25 volts, voltage on the capacitor is 0. What about current? What about the current on the two resistors? Well, the current equals V over R. So I1 is going to be the voltage 1 over R1. I2 is voltage 2 over R2. Okay, so we plug in the values there, and you look back and see that there was 250 ohms for R1, so that's going to be 25 volts over 250 ohms, so that's going to be equal to 0.100 amps. The other one is 25 volts over 350 ohms, so that turns out to be equal to 0.0714 amps. So now we have the voltages on everything. What about the current in the capacitor? It's in series with I2, so that means it's going to be charging at a rate of 0.0714 amps. Now, the next question is, if it's charging, then what is the voltage and current after it has been charging for a long time? Okay, so after a long time, now what is a long time? Long time is a relative term. A long time means long enough for the capacitor to be charged. How long is that? Well, it depends on the time constant. You know, normally you'd say if you wait like 10 time constants, then there's like virtually nothing much left you can do to it. Okay, you know, often you just say like 4 or 5 time constants is pretty well charged. But still, if you wait 10 time constants, you know that there's almost nothing left to change, and so that'd be a long time. So it just depends on how long the time constant is. But after a long time, then what is V1, V2, VC, and what's the current I1 and I2? Well, notice there's no change right here. So the voltage is the same as it was before, 25 volts, which means that the current through that first resistor is still the same, 0.100 amps. Now, what about for the other one? If the capacitor is charged, there's no more current flowing in the capacitor. So that means the current in the capacitor is 0. If it's fully charged, it's going to be whatever the maximum charge is going to be. So it's going to be at 25 volts. Now, what about the voltage on resistor 2? Well, the total across the entire thing is 25 volts. So if you got 25 volts already across the capacitor, there's nothing left. So that means once it's fully charged, the current is 0. There's no current. V equals IR. Therefore, you know that the voltage has to be 0. So that means even though there's voltage on the capacitor, there is no voltage on R2 once the capacitor is charged. If there's no current going through it, there is no voltage. Okay, now, next question. How long did it take for that capacitor to get halfway charged? Okay. So how long did it take after we closed the switch for that capacitor to be halfway charged? Well, the current charging the capacitor is doing this. So that means that it's only going through that resistor. It's only going through R2. Okay, so that means that if we're charging, Q equals Q max 1 minus e to the minus t over tau. So now what is tau? Tau equals RC. So that's going to be equal to, it's only going through that one resistor, so 350 ohms times 150 microfarads. Okay, a micro 10 to the minus 6. So this turns out to be 0.0525 seconds. Okay, so that means how long, if it's closed for a long time, how long is a long time? 10 time constants. That means for this circuit, half a second is considered a very long time. Okay, so if it's fully charged, okay, that's Q max. So if it's half charged, Q equals 1/2 of Q max. So we can say 1/2 QM equals QM 1 minus e to the minus t over tau. Okay, so the QM's cancel. And so we would say, well, in that case, we can do a little bit of algebra, say that e to the minus t over tau equals 1/2. So minus t over tau is the natural log of 1/2, or t equals minus tau natural log of 1/2. So t is going to be minus 0.0525 seconds times the natural log of 1/2. So the time is going to be equal to 0.0364 seconds. That is how long it takes to get halfway charged. Okay. Now, so we got the switch, and the switch was closed. So the next question is, I want to open the switch, and what's going to happen? What's going to happen is the current's going to start flowing that way. Okay, and so I'm going to ask the exact same questions. What's the initial current in each resistor? You know, what's the voltage, and so forth. Now, in this case, it's pretty straightforward because we know that the initial voltage on the capacitor, is going to be 25 volts. Okay, so R1 and R2, so they're in series, so it's just going through there. So when you first open the switch, then the current is going to be in one loop there. So I1 equals I2 equals IC, and that's going to equal 25 volts divided by R1 plus R2. So that's 350 ohms plus 250 ohms. So that means the current is all going to be the same, 0.0417 amps. Now, what about after a long time? Before we look at what happened in the future, we might also be interested in knowing what is the voltage on each of those things. So what is the voltage on the 350 on voltage 1 and voltage 2? Well, that's just going to be equal to IR. Okay, so IR1 and IR2. Okay, so that would be simply equal to 250 times the 0.0417. So that's going to be equal to 10.4 volts, and the other one is going to be equal to 14.6 volts. If we did it right, those two should add up to the total voltage of 25 volts, which they do. Okay. After a long time, then what? Well, after a long time, the capacitor is discharged. So the voltage in the capacitor is 0 and the current is 0. If the current is 0, that means that the voltages are 0. So that's pretty straightforward. So the next question, though, is how long until it is 75% discharged? Well, that means the Q is 0.25 of the initial. Now that's important. It's not 0.75 of the initial. That's a mistake the students make on a test all the time. It's 0.25 of the initial because it's 75% gone, 75% discharged. So now Q equals Q naught e to the minus t over tau. Now what is tau? That's RC. So RC is going to now be the total 350 ohms plus 250 ohms times the 150 microfarads. So the tau is going to be equal to 0.090 seconds. All right. And so Q equals 0.25 Q naught. So that means 0.25 Q naught equals Q naught e to the minus t over tau. That cancels, so that means with a little bit of algebra, we can see that natural log of 0.25 equals minus t over tau. So t equals tau times natural log of 0.25, negative of that. So t equals minus tau 0.090 seconds times the natural log of 0.25. So the time it takes to get 75% discharge is 0.125 seconds, so 1/8 of a second. And so that's how you do this problem. So I talked a little bit fast in order to get this to fit within the time frame that YouTube lets me put on here. But this gets an example here of a problem that there's multiple steps that we can do with this one problem. And so that's kind of how you approach it. Think about it long term, short term. The instant you close the switch, what's it doing? Long term, what's it doing later? So this is a circuit that's changing as you're studying it. It's not staying put. It's not a static circuit. This is a circuit that's changing. Now that's something that you need to keep in mind because we're going to later be talking about AC circuits, and they're all about changing. And so for now, we're just starting the process of RC circuits, charging and discharging. In fact, that's what we call these things, is RC circuits. Either charging or discharging and with capacitors.